Okay, hello everyone. Today I want to talk a model that I found in this paper. Actually, in this paper we can find two model. First, physics informative neural network or machine learning model, and the second is here FullSWOF 2D model. It's a full shallow water equation for overland flows. I think this is something like a runoff model. And after I explore a bit in this model, I find it quite interesting. So that's why in this video I just want to explain about this FullSWOF two-dimension model. In the next, maybe I will try to combine it with PIN or physics informative neural network, but I don't know, maybe. And in here you can download the model. I will just put the link of this I will just put the link of this I will just put the link I will just put this link in the description of this video. And in here you can find to file the zip and WinZip. The zip in here, I think this is the version for the Linux, because when I download this I found a shell script, and I think it's for the Linux. And WinZip in here, this is for the Windows version, because my PC is a Linux version, so I will just download the first link in here. And to install that, it's quite easy. When you Google it, you will find this file, and you will find the documentation of FullSWOF 2D like this. And for the installation, it's quite simple. We just make this clean and make, and then after that you will find the binary code here. Here you will find this. And then after you find this, usually to make your life easier, you will put this FullSWOF to the binary to the path. How to do that? It's something like this. So nano bus rc. Here I just append the path directory of this FullSWOF 2D to the path variable in here. And then after that you can use it. Oh yeah, in this video I don't have a case that I want to run, but when you install this FullSWOF 2D, you will find this example. So in this example you can run, or you can just test run the binary code. And in this video I will use this inhomogeneous boundary. Here we have input and output. Output in here will be a directory where when we run the model, all of the file that will be outputted will be put in here. And in here we have several files, but to adjust the parameters, of course we adjust it in this parameters.txt. And in here you will find many configuration, but I think in the configuration in here is the most important, because here in the line 5 we have number grid cell with respect to x. So it's the total grid in the x direction or in the horizontal. Here the default is 32, and the number grid cell with respect to y or the horizontal or the latitude, it's 64. And here the length of the domain with respect to x. So this is the length of the entire domain that we have in here. So it's in meters, so it's 6.4, and for y it's 12.8. So actually, if we have this data, we can calculate the width, and we can calculate the width and height of the single grid. So it will be, for the width will be 0.2, and for the height it will be also 0.2. And in here, this is the final time, or the final time step that we can find, or we can find when we run the model. And this is the number times effort. So this is like how many snapshots that we want to create when we run this model. So if the final time is 50 and number of times effort is also 50, then we will save the snapshot of the output of the model for every 1 second. And here, this is the choice of the time step. So usually people will just treat the number of times effort as the time step, but no, this is just how many snapshot, or how many snapshot that we want to create. The real time step is here. So here we have two options, fixed CFL and fixed DT. Yeah, fixed DT in here, it's something like it's quite simple. So if we choose fixed DT, then for example we set it 0.2, then for the time step 1 it will be 0, time step 2 it will be 0.2, and time step, wait, I think I am wrong, but yeah, I still don't quite understand how to set it as fixed DT. But if we using the fixed CFL, the time step or the DT that we will use in this model will be automatically adjusted with the shape of the grid point that we have. So as you can see, we already calculate the width and the height of the single grid point. It's 0.2 times 0.2. So to make the model stable, the time step will be adjusted to make it matching with this. If you want to understand about what I talk about the CFL condition in here, just Google it. It will be quite long if I explain it in this video. And this is just the configuration for the boundary. I am not yet explored it, but yeah, this is I think this is one of the important configuration. So here we have a topography. We have 3 options in here. I don't know about the tacker, but for the option 1 file, we can provide a file for the topography. Maybe we can provide a bathymetry, but in this example case here, the topography.txt already served, ready to use. And flat is, there's no topography, just flat surface. And then after that, we have rain.txt. Rain.txt is, the file is something like this. So in here, this is the time, and the second row in here, this is the rain intensity. So here in the time 0, there's no rain, and then at the 35 seconds. After that, there will be rain intensity like this, and then the rain intensity after in the 50 seconds will be changed in something like this. So because we only run the model just up to 50 seconds, I think what we care about just this value here. So maybe in the 0 to 34 seconds there will be no rain, so there will be no significant change in the surface. But after 35 seconds there will be some change in the output. And then here we have a hoof. I think this is just something like initial condition for the model. And BC in here, I think this is the boundary condition configuration. Let's just let it be. Okay, let's run this. Yeah. Okay, done, and the output will be in here. As you can see, it's already updated to our latest run. So here we have a several file and maybe you will think that the file is the result will be in the result.dat in here, but no, this is just some statistic for the run. Actually the output is in here in the whose final.dat. So this is the result of the last time step or in the 50 seconds. Remember that we said that this model will run until 50 seconds, right? So actually this is a GNU plot file, so you can use a GNU plot file to plot this. Let's test. And you will find something like this. So this is the result of the model that we ran earlier. To understand why the result is something like that, we must understand the input, especially for the topography, you know. Okay. So the topography is like this, and the final dot is like let's match the coordinate to understand this. And yeah, as you can see here this is our topography. So as you can see in this part, this is the deepest part, right? And this is the shallowest part. And when we run the model, actually it's a runoff model, so one of the parameter in that model is water depth surface. So when we run it, because this is the deepest part, when there's a rain, so it will be naturally the most depth part will be in here, in this point, and that is what happened in here. This is why the value in this part is it's a quite high if we compare it with the another point or part in the 3D in here. So I think that is the explanation for that. We set the number times of saved of or the evolution. All of that is saved in here. So that's why the size of this file is so big if we compare it with the final, because in here we have the 50 snapshot of the running model. Actually I didn't want to open it because it will make my computer laggy, but actually I already plot that using GNOplot and resulting something like this. So this is the evolution from the evolution.dat, and as you can see here in the rain, see, and the time step from 0 to 34 there is no change, right? Because there is no rain. But after 35 there is a change, right? This is because we set the rain happen after 35 seconds. Okay, I think that's all. I think that's all for this FullSWOF 2D model. Thank you. Bye.